Good morning, geometry scholars. We're going to be talking about our third type of rigid transformation today. And in order to do that, I thought we would start with a motivation of a real life STEM video. This is a revolving door.
Yes, perfect location.
Yeah, this is pretty nice, but wait, what does this have to do with rotational symmetry?
Rotational symmetry allows us to use land more efficiently.
Okay, I'll bite. What are you talking about?
Okay, so you see the skyscrapers?
Yeah.
The skyscrapers use land more efficiently than all of these small buildings.
Oh, okay, yeah, I can see that.
Yeah, but the problem is skyscrapers need elevators. Otherwise, we'd waste a lot of time climbing stairs.
Hey, you don't get fit and trim like this just standing around in an elevator.
Whatever. The problem with elevators is that they create a chimney effect. So the air pressure inside of an air-conditioned building is greater than outside.
Okay.
So how do you keep the doors closed?
It's easy. Locks. Duh.
No, revolving doors.
Oh, okay. I think.
Okay, so a hinge door does not have rotational symmetry.
Okay.
See? You're not symmetrical.
Right. What? Hey.
No, not you, your shape.
Oh, okay, I see, yeah.
Shapes that look the same when turned on a point have rotational symmetry.
Okay.
So, put your arms out like a revolving door.
Oh, okay. Equal on each side?
And you move 180 degrees. You look the same, more or less.
Oh, okay, I get it.
So remember when I was saying that there's different air pressures?
Right.
The hinge door moved because there's pressure on only one side.
Oh.
But a revolving door, there's pressure on both sides.
So it's equal, right?
Exactly. It's equal, so it doesn't move.
Okay, but it seems a bit too simple. I mean, does it really work?
I made a model to demonstrate. Follow me.
Okay.
See? The model is divided into two parts, and the marbles represent the air pressure pushing on the doors in the middle here. When the board is flat, there is no air pressure on the doors, just like when the air pressure is equal on both sides.
Okay.
But when you tilt the board up, the marbles push through the doors.
I see. And if we turn the revolving door manually, it easily lets the marbles through, just like a normal door.
Exactly. Revolving doors have rotational symmetry. So if you turn them 90 degrees or 180 degrees, it's the same.
Well, there you have it. A complex problem solved by simple geometry. You know what? I will never look at revolving doors the same way again.
Good.
So that's our motivation for rotations. And the thing is, if we were together, we would be doing it differently. So this distance learning thing is going to be slightly different. So the first thing we're going to do is look at some of our vocabulary. So hopefully at the end of this 15 or 20 minutes, you're going to perform rotations, perform compositions with rotations, in other words, do the numbers, and of course, identify rotational symmetry, which some people get right away and some people have to practice a little bit more. The things we'll talk about are the center of rotation, the angle of rotation, rotational symmetry, and the center of the symmetry. I know for a fact you all know examples of symmetry. So let's just start here. So it is a transformation, as I mentioned, in which a figure is turned about a fixed point called the center of rotation. Rays drawn from the center to a point and its image form the angle. So you always have to know like how much you're spinning. Okay, if the center of something is here and you start here, then this is 90 degrees, 180, 270, and it goes all the way around to 360 and it keeps going again. So just like in our other transformations, the original pre-image is written without a prime mark. And then after you do the transformation, the new one has the prime. So there's two different parts of a rotation. You have to mention where it's centered and how far you've gone, as well as which direction, because you can go clockwise and you can also go counterclockwise. So you see the pictures here. If this center is on the figure, then the center Q is equal to Q prime. So if it's actually on it, just like when we did reflections, it doesn't change. But if it's not on it, then Q and Q prime will be different. That's what that says. So now if we're going to draw one, this is how you do it manually, which again, if we were going to do it in class, I would give you a protractor, I would give you tracing paper, and I'd show you how to do this step by step. It's going to be different, but I am going to show this to you. Okay, so
draw a 120-degree rotation of triangle ABC about point P. Solution. Step 1. Draw a segment from point P to point A. Step 2. Draw a ray to form a 120-degree angle with segment PA. Step 3. Draw point A prime so that PA prime is equal to PA. So you want the distance between points P and A prime to be equal to the distance between the points P and A. Step 4. Repeat steps 1 through 3 for each vertex. Draw a segment from point P to point B. Then draw a ray to form a 120-degree angle with segment PB. Draw B prime so that PB prime is equal to PB. Next, draw a segment from point P to point C. Then draw a ray to form a 120-degree angle with segment PC. Draw C prime so that PC prime is equal to PC. Draw triangle A prime, B prime, C prime by connecting the vertices. So triangle A prime, B prime, C prime is a 120-degree rotation of triangle ABC about P.
sorry about that with the words right in front of the drawing, but you can see you measure the distance and then you move it. You measure the distance and then you move it. You measure the distance and you move it. And that's really all there is to it. But the 120 degrees we're not used to using. So when you do perform a rotation, you can rotate it any more than 180 degrees. This is where you can see if we started at A, the blue dot, then if you went 130 degrees, it would end up at A prime. If you went 220 degrees from the blue, it would end up at the green, A double prime. And if you went 310 degrees, and these are all around the origin, so all from here all the way around, that's 310 degrees. So if you rotate something 360 degrees, it goes exactly to the same place. Therefore, it maps a figure onto itself. So now here's the thing. You can actually do just coordinates, which is easier in the sense that you're going to just do the equations. So you can rotate. Normally we'll do counterclockwise, but you can also do counterclockwise if you say you're going counterclockwise, so that angle is going to be a little different. So these are the rules that we've written in our other notes. And if you know the original AB, this is an XY coordinate, then if you rotate 90 degrees, all it's going to do is switch the A and B and make the B negative. But it's going to be like the same height as the X and it's going to be exactly the same place on the circle if it's rotated around the origin. So your AB would turn into negative BA. Your AB for 180 is going to come all the way down here, and it's going to be exactly negative, both of those values. And if you go 270, which is almost all the way around the circle, we're talking 3 more quadrants, then your AB is going to switch again but it's your A that's negative. Because think about this. Both coordinates here are positive. Here the x coordinate is negative, but the y is positive. So you already know this, these coordinates. Third quadrant, everything is negative, and fourth quadrant, the x value is positive, but the y value is negative. So that should help you remember those rules. Otherwise, they can seem confusing, but just remember you already know the quadrants. So here's another performing on how to exactly do it.
Graph quadrilateral RSTU with vertices R31, S51, T5 -3, and U2 -1, and its image after a 270-degree rotation about the origin. Solution. Use the coordinate rule for a 270-degree rotation to find the coordinates of the vertices of the image. Then graph quadrilateral RSTU and its image. For a rotation of 270 degrees about the origin, the point AB maps to the point B -A. So the point R31 maps to the point R prime 1 -3. The point S51 maps to the point S prime 1 -5. The point T5 -3 maps to the point T prime -3 -5. And the point U2 -1 maps to the point U prime -1 -2. Now graph each quadrilateral. Graph R31 S5.
And this is again where color will really come in handy. So make sure you have your colors or highlighters ready.
1, T5 -3, and U2 -1. Connect the vertices to form quadrilateral RSTU. The image after a 270-degree rotation about the origin is R prime 1 -3, S prime 1 -5, T prime -3 -5, and U prime -1 -2. Connect the vertices to form quadrilateral R prime, S prime, T prime, U prime. So quadrilateral R prime, S prime, T prime, U prime is the image of quadrilateral RSTU after a 270-degree rotation about the origin.
So one thing I want you to notice about these is that with a reflection or a translation, even though it's rigid, you can sort of visualize it. With these rotations, they're much more difficult to visualize where the other point goes. And that's why it's really important for you to just use the rules. You'll get it right every time, and you won't pull your hair out in frustration, okay? So we only had a couple of examples. We're going to be doing some of these together under the camera, but there is a postulate, 4.3, of rotation is a rigid motion. We've already been talking about that through the rest of the chapter. Now, there is what's called a composition, and composition just means more than one rigid motion at a time. So you could like translate and then shift, then rotate, or you could rotate and then do a symmetric flip. So that's all it means, is that when you do more than one thing at a time, they call them compositions. So again, they look a little more crazy, but keep your rules and do step by step, and you'll be fine. So, because a rotation is a rigid motion and a rigid motion preserves length and angle measure, the following statements are true. So you can move things. The composition theorem, 4.1, guarantees that composition of rotations and other rigid motions, such as translations and reflections, are rigid motions, which means you can do any three of those or combination, and it will still be the same size and the same shape. So here's how you can actually do one, again, step by step.
Graph segment RS with endpoints R1 -3 and S2 -6 and its image after the composition. A reflection in the y-axis followed by a rotation 90 degrees about the origin. Solution. Step 1. Graph segment RS. Graph R1 -3 and S2 Unless you are told otherwise, perform the transformations in the order given. So step 2, reflect segment RS in the y-axis. A reflection in the y-axis maps the point xy to the point negative x, y. So the point R1, negative 3 maps to the point R prime, negative 1, negative 3. And the point S2, negative 6 maps to the point S prime, negative 2, negative 6. Segment R prime S prime has endpoints R prime, negative 1, negative 3, and S prime, negative 2, negative 6. Step 3. Rotate segment R prime S prime 90 degrees about the origin. Rotating 90 degrees about the origin maps the point xy to the point negative y, x. So R prime, negative 1, negative 3 maps to the point R double prime, 3, negative 1. And S prime, negative 2, negative 6 maps to the point S double prime, 6, negative 2. The segment R double prime, S double prime has endpoints R double prime, 3, negative 1, and S double prime, 6, negative 2. Segment R double prime, S double prime is the image of segment RS after the given composition.
So again, see how every step is very careful. Sometimes you'll want to do some of these in your head, but it's really hard. So just get in the habit of writing them down and using colors, and you'll do fine. I believe we are ready to go to symmetry. So now you've all seen this. A good logo has great rotational symmetry. So you've been bombarded with rotational symmetry actually most of your lives. So a figure in the plane has rotational symmetry when the figure can be mapped onto itself by either a rotation of 180 degrees or less about the center of the figure. This point is the center of symmetry. Note that the rotation can be either clockwise or counterclockwise. For example, this figure has rotational symmetry because you can move it 90 or 180 so that it maps onto itself. But if you only move it 45, then it looks different. See, it looks shifted from here to here, but it looks the same from here to here or here to here. So that's all we're going to do with that really is identify it. And here's an example.
Does the figure have rotational symmetry? If so, describe any rotations that map the figure onto itself. A. Parallelogram. B. Regular octagon. C. Trapezoid. Solution. A figure has rotational symmetry when the figure can be mapped onto itself by a rotation of 180 degrees or less about the center of the figure. Part A. The parallelogram has rotational symmetry. The center is the intersection of the diagonals. A 180-degree rotation about the center maps the parallelogram onto itself. Part B. The regular octagon has rotational symmetry. The center is the intersection of the diagonals. Rotations of 45 degrees, 90 degrees, 135 degrees, or 180 degrees about the center all map the octagon onto itself. Part C. The trapezoid does not have rotational symmetry because the center is the intersection of the diagonals, and no rotation of 180 degrees or less maps the trapezoid onto itself. Notice you would have to rotate the figure 360 degrees to map the figure onto itself. So the trapezoid does not have rotational symmetry.
Okay, so what you'll be doing, in the Big Ideas homework, is you will be deciding whether it does or not. So again, just find the center and see if you can rotate it 180 degrees or less so that it looks exactly the same as you started. If you do, then you have symmetry. So again, we might be doing some of these in class, but I'm trying to keep this video short. And here we go to the exercises. So you are assigned some homework in Big Ideas, and we'll be also keep your notes with you. Get some graph paper and colors and a straight edge, and I will see you soon in class.